Ladies and gentlemen, welcome to my third tutorial of my lecture series on Fractal Finance. In this tutorial you will learn how to estimate the Hurst exponent by means of rescaled range analysis as proposed by Benoit Mandelbrot. I have broken the code down, respectively the estimation procedure down into 9 different steps. By this you learn how to implement this procedure into a computer program such as Matlab, which is what we will do afterwards. So let's get started. Let's assume we have a data vector x, and x can be anything. As argued by Mandelbrot, the rescaled range analysis does not require a certain distribution of the underlying process. So the first step of rescaled range analysis is that we have to determine, okay, how many cluster categories do we have? In the lecture series we had a data vector having 1024 observations, and I told you it must be the length of the data vector should be a multiple by 2. And I argued also in the lecture, if we have a data vector of 1024 observations, okay, we can operate with I equal to 8 categories. So how can we come up in general with the corresponding number of categories that we can operate with given a data vector? So in general, we have to take the logarithm of capital T, the number of total observations in the data vector, over 4, divided by the logarithm of 2. And if you plug in 1024, okay, you should have here an even number, and it should be 8. So that is how you can think of. Given that we have 8 categories, the cluster size of each category is then given by 512, 256, 128, 64, 32, 16, 8 and 4. So you see all of the cluster sizes, if you is a multiple of 2. If you multiply 4 by 2, we have the cluster size 8. Multiplying 8 by 2, the cluster size is 16. And so on and so forth. So all of these cluster sizes are multiples of 2. This is important to bear in mind. And we want to have at least 4 observations in one cluster. So this is how you can think of why I argued in the lecture series it should be a multiple of 2. So the next question that we have to deal with is how many observations per cluster size k. Okay, and we know already here how many observations do we have, but the program does not know. Okay, so we have to take it in small steps. So in general, the formula how we can think about it is capital T over 2 to the power of I. You see obviously the number 2 plays an important role in rescaled range analysis. So for example, if I is 1, and using this formula here, what we get is capital T over 2 to the power of 1, since I is now 1, and that's equal to 512. So that is our first cluster size. So what's the next cluster size? In the same manner, we have to calculate capital T over 2 to the power of 2, which is 256. Once we have determined how many observations per cluster size k we have, the third step is then that we have to store the results. Operating with 8 categories of clusters, we have the 8 by 2 matrix, where we store in the first column the corresponding rescaled range statistic RS bar for category K, and on the right hand side, the second column vector, there we store just the corresponding size of the cluster K. And in the lecture we also discussed why this should be RS bar. We come back to that later. So we have to take the average of this rescaled range statistic for each of the clusters. So you can also think about how this might look like if we have more or less than 8 categories. The fourth step is then that for each cluster category I, which is from 1 to 8, we have to determine how many clusters J do we have. Now this might be redundant for you, but not for the program, because the program does not know that. So we have to tell the program how many clusters do we actually have. And it is quite simple. Again, the key number here is 2. We have to take 2 to the power of I. For instance, if I is 1, 2 to the power of 1 is simply 2. And now remember, we have to end up in each of these iterations with the final sample size, which is 1024. So for instance, we know that we have, if we have the cluster size 512, we have J is 2 clusters, and 2 times 512 must be equal with 1024. In the next iteration, if I is 2, how many clusters do we have? 4. Because 2 to the power of 2 is 4. And 4 times the cluster size, K, which is 256, is again 1024. And in the same manner, obviously, if I is 8, then we have to multiply 8 with, we have to take 2 to the power of 8. And this should be, we have to multiply this with 4, right? And we end up with 1024. So this is how we have to think about it. The next steps that follow, we have to repeat in an iterative manner for all cluster categories. The fifth step is then, and this has to be done again for all cluster categories I, for example, let's start with I equal to 1. We have to store the rescaled range statistic for all subclusters. So we said when we have the cluster size K is 512, we have 2 clusters. J is equal to 1 and J is equal to 2. So we get, obviously, for that cluster size, 2 estimates for the rescaled range statistic. For each subcluster, we get 1 rescaled range statistic that we have to store in some vector. Obviously, in the next iteration then, if you think now for the next step, if I is equal to 2, then we have obviously 4 rescaled range statistics that we have to store in some vector. And then later on, we have to take the average of that vector here. That we then store in the other vector, in the 8 by 1 matrix. So that's the way how we have to think about it. So we have to select the clusters from the corresponding data vector. And we have here a very general data vector that has the dimension 1024 by 1. And this vector here is in its transposed form. So it's a 1024 by 1 vector. So what do we have to do with that vector here? So the next step, the sixth step, is then we have to compute the demeaned subvectors. So we know that our cluster size in the first iteration is 512. So that means we have to divide our data vector in 2 subvectors that have the dimension 512 by 1. So what we do first is we take the first 512 observations here. And what we have to do is we have to take the sample average of that vector here. Let's denote it as x bar 1. Then we have to subtract from each single element here in that vector, in that subvector, we have to subtract the corresponding sample mean of that subvector here. And this is what we have done here. yeah, we have denoted as, let's denote this vector here as x1. We just subtract from x1 x1 bar. And the dimension of the vector here is, as I said, it's 512 by 1 vector. The same thing we have to do for the second subsample. We take the observations 513 until 1024. That's our second subvector for the second cluster. And we compound the sample mean from this subsample here. Yeah? And that is what we refer to as x bar 2. And then again, we just consider the second subsample for itself, and we subtract from each single observation the corresponding subsample average. Now let's denote this subvector here as x bar, or as x2. So what we have to do is we have to compute x2 minus x bar 2. And again, the dimension of the vector here is the same like from the first subvector. It's 512 by 1. Yeah, now we can think about how we would proceed in the second iteration when I is 2. So again, we would have obviously 4 rescaled range statistics. Why? Because our k is then 256, and we have to divide our data vector into 4 subsamples, and each subsample has the length of 256. Yeah, it is straightforward. And then obviously we have for each, we have here obviously then 4 d-meaned subvectors to deal with. Once we have computed the vector of d-meaned returns, the 7th step is then that we have to compute the cumulative returns. Since we have in the first iteration 512 observations in each of these 2 clusters, so we have to compute this for both clusters. So in the first subsample cluster, it might look like that evolution, and for the second subsample cluster, the evolution of the cumulative returns might look like that. The 8th step is then that we have to take the range of between maximum and minimum, and we have to divide it by the corresponding standard deviation of the subsample data vector. Yeah? So how do we proceed? So once we have computed the cumulative returns, we just determine the maximum and the minimum. Yeah? So that's the corresponding range for the first subcluster. So, and then we have to divide it by the corresponding standard deviation of the corresponding d-meaned return subvector. And we have to do that obviously for both of the clusters. The 9th step is then that we have to take the average for all clusters J given cluster group K. Obviously, the rescaled range statistic given cluster group K is the difference between maximum and minimum of the cumulative return divided by the corresponding standard deviation that we have seen in the previous step. Yeah? So, given that we have cluster group K is 512, we have, and capital T is 1024, we have 2 clusters, as we have seen. So we have stored the corresponding rescaled range statistic, and then we have to take just the sample average of that vector here. This is then stored in the corresponding 8 by 2 vector that we discussed earlier on. Yeah? So the average of that vector here is this guy here, RS bar, for category K is 512. And then we have to take the natural logarithm of the sample average, or of this corresponding average of that data vector. And on the corresponding right hand side of that matrix here, the first element in the element in the first row is then simply the natural logarithm of the corresponding cluster size, which is 512. So in the next iteration then, if I would be equal to 2, obviously this vector here would then expand, yeah, because we have then 4 categories, okay. So we have then obviously we have to compute 4 rescaled ranges, yeah, and the size is then, the corresponding size is then 256. All right, 256, and we have then obviously 4 clusters or subclusters. And then the next, we would then basically take the corresponding average of 4 rescaled ranges, given the cluster size 256. Yeah, and again, we would store it then in this 8x2 matrix as in the second row, which would be then the logarithm of RS bar for cluster size 256. Again, we take the natural logarithm of the sample average, and the next element would be then simply the logarithm of 256, as this would be the next cluster size. Yeah, and we do this obviously for I is 1 until I is 8. Yeah, here obviously I is 1, here I is 2, and we would do this until I is equal to 8, until our data matrix is completed. And now let's have a look on how to implement this in Matlab. Here I have already opened the corresponding Matlab script entitled RS analysis for a given vector x. First of all, we have of course to define what is our data vector that we wish to investigate here. Then we have to define the sample length, and as we discussed on the whiteboard, it must be a multiple of 2. So capital T is the length of our data vector. Here I have already uploaded one data vector x, which has a length of 1024 observations. So if we copy this command here into Matlab, yeah, without the colon, then we will see what it is 1000. It will give us 1024 as the number of sample observations. Then we have to define the categories. How many categories of clusters K do we have? All right. So in the formula, like on the whiteboard, is the logarithm of the capital T observations over 4 divided by the logarithm of 2. And once we do that, let's copy that into our command window. It should give us a number of 8. So next is then we have to store the results in a data matrix, because we need these data for running our log-log regressions later on. So we first create a matrix that has 0 entries, and since we have 8 categories, we have 8 rescaled range statistics, respectively averages of rescaled range statistics depending on the cluster size. Yeah. So our data matrix where we store the results in has to have the dimension of 8x2, since we have 8 categories. So this is what happens here. So the matrix that pops up here has 0 entries. And in each iteration, we want to store results here. Yeah? Here in the first array, which is the row 1, column 1, we want to store for the first cluster size the average rescaled range statistic. Whereas here, in the second element of the first row, we want to store the corresponding cluster size. Yeah, and we do this obviously for all 8 categories. So let's get started here. We go through iterations I is 1 until 8. We know categories is 8. We have defined it as 8. So we do this here 8 times. In 8, this for loop here has 8 iterations. And in each iteration, we store the result in the corresponding result matrix. First of all, we have to define the number of subsamples, and like we discussed on the whiteboard, it is 2 to the power of I, iteration I. In the first iteration, let's just consider the first iteration when I is 1. Number of subsamples is then what? It's 2 to the power of 1 is 2. That means we have 2 subsamples to deal with. And for each of these subsamples, we have to calculate the rescaled range statistic. So next, how many observations do we have per subsample? It's, for us, of course, self-evident. It must be 512, but the computer doesn't know that. We have to define it here as capital T divided by the number of subsamples. Since in the first iteration, the number of subsamples is 2, and capital T is 1024, it follows that the observations per subsample must be 512. So then, as we discussed on the whiteboard, we have to store the intermediate results in another matrix, respectively vector. So this is what we do here. The sub underscore result underscore 1. Here we store the corresponding rescaled range statistics for each of the subsample clusters. So in the first iteration, when I is 1, we operate with 2 clusters, right? Each has the size of 512 observations. So here in the first, when I is 1, this obviously must be a 2 by 1 vector. Okay, let's say, to give you an example, let's set I equal to 1. So then this should be, obviously, the number of subsamples should be 2. You see, this is exactly what comes out. Observations per subsample should be 512. You see. And the sub-results, this must be a 2 by 1 vector, which has 0 entries. And you see, this is exactly what we have defined here. Then we have to do something for each of these subclusters. Okay, we know each cluster has 512 observations in the first iteration. So J is 1 to 2. And we have to do something, and this is what we see here. We define the vector x1. If J is 1, obviously we have defined the first subcluster. So J is 1. 1 times observations per subsample is 512. So 512 minus observations per subsample is 512 minus 512 plus 1 is 1 until 1 times observations per subsample, this is 512. So obviously the vector x1, if J is 1, this guy here gives us from the original data vector x the first 512 observations. Okay, so then we define a second vector here, and recall we are still in this for loop here, in this for loop when J is 1. So we define a second vector x2, and what should it be? It's this vector, the subvector x1 minus the mean of x1. Okay, so this is our demeaned vector of observations for the first cluster of data. Then we define a third vector x3. It should have zeros. and the length of that vector here should be equal with vector x2. Of course, we know already that the length of x2 is 512, right? Because each of these subclusters has 512 observations. And it has, obviously, it's a column vector, so the dimension here is of an x3 is 512 by 1. And what we do here is we want to store the cumulative sum of the mean returns. So we set the first element of x3, the first element here, is the same like an x2. Now, this is what happens here. We set it to be the same elements. But then, from element 2 to the last element, we have to add, obviously, we add to the first element from x3 in this for loop here, the corresponding element from the previous time period plus the element x2 from k1. So, okay, let's do that here. Let's set j equal to 1. And let's run this loop so that you can see what happens here. So let's consider x3. Let's plot x3. So this is what happens. So this is the cumulative return path for the first subsample, you see, and 512 observations. So obviously the rescaled range statistic is then obviously the maximum, which is here, and the minimum is here. So the difference between this time point and this time point divided by what? By the standard deviation of x2, which is the d-mean series. Let's plot x2 also so that you see that this is should be a stationary process, and this is usually what it is. Yeah, so we have to take the standard deviation of this guy here in the denominator. So again, so what happens here? X4 is the range between the maximum of x3 minus the minimum of x3. This is what we just have seen. Then we store in the sub underscore results underscore 1 vector, the first element, you know, we are in the first cluster here, j is 1, is what? It is the range between the maximum and the minimum of the cumulative data vector for the first subsample cluster, divided by the square root of the variance of x2. Okay, let's do that. Now we have stored here in sub-result, the first element here is obviously 108.97. So we have to do the same thing for the second cluster, for the second subcluster, to the last 512 observations. And this is what we do here. We have now set j equal to 2. Let's copy this. And now you see we have stored also the second result for the RS statistic. We can also plot the cumulative return path for the second part. You see here. This is for the observations 513 until 1024. Yeah, so we have to take the maximum, which is here, and so the range from here to here. This is the sample minimum, and we have to divide it by the square root of the vector x2, which looks now like that. So this is what happens here. Then what we do have to do is, okay, we have to take the mean of the sub underscore result underscore 1 vector and the logarithm of the mean. In the same way, again, we have to take the logarithm of the cluster size, which is 512 in the first example. So let's copy this into the command window so that we can see what comes out here. if we now check this result matrix, we should have the average of these two numbers here and the logarithm of the average. And this is obviously 4.75. And the logarithm of 512 must be 6.23. This is exactly what we have stored here. So in the same manner, we can do the next iteration. Then I would be equal to 2. All right, if I is equal to 2, let's set I equal to 2. We can again copy what is here in that loop, and we will hopefully see that now we have stored here obviously the second result. Yeah. So the averaged rescaled, or the logarithm of the averaged rescaled range statistic for the cluster size k is equal with 256 is 4.1158, and the corresponding logarithm of the cluster size to the logarithm of 256 should be 5.5452. So in the same way we go through it until we are on the last category, which is the 8th category. Okay, so and you see obviously, as we discussed on the whiteboard, this sub underscore result and underscore 1 vector where we store the intermediate result increases in each iteration. Here we have already in the first iteration we had it was a 2 by 1 vector. Now it's a 4 by 1 vector, and in the next iteration it would be an 8 by 1 vector, and so on. In the last iteration, this guy here is a 256 by 1 vector. Yeah, because if 2 is in the last iteration, we have 2 to the power of 8, 256 subclusters. So let's copy the whole code, okay, and into Matlab. And now we have here, you see, let's check the result matrix. Here is our result matrix. Now we have 8 entries and 2 columns here. Yeah. So in the first column vector, we have the corresponding logarithm of average rescaled range statistics given each cluster size in logarithms. So, and how do we proceed now? As we discussed in the lectures, we have to regress the logarithm of the average rescaled range statistics on the logarithm of the cluster sizes. Yeah? We have to do a log-log, so-called log-log regressions. So we set our dependent variable. The dependent variable is our y variable in the OLS framework. This is the first column vector, yeah, of our results matrix. Yeah? Recall, the first column vector here, we have the logarithm of the average rescaled range statistics given the cluster size k. The independent variable is obviously then the logarithm of the corresponding cluster size, which is in the second column here. Yeah, it's the second column of the result matrix. So then we can define the regressor matrix X in the standard OLS framework, right? And we define it as what? We need a vector of ones, which should have the length of our dependent variable, which is 8. Okay, so it's a vector. It's an 8 by 1 vector of ones. This is what we have defined here. And in the second column of our X matrix is simply our independent variable, which corresponds to the logarithm of the cluster size. Okay, this is what happens here. Let's just copy that into Matlab. Yeah, so if we now check the regressor matrix, it should look like that. Yeah, very simple. What we have to do then is, okay, let's get the point estimator, because we want to know what's the Hurst exponent, right? So H1 is defined as what? It's the regressor matrix transposed times itself inverted times the regressor matrix transposed times the dependent variable. Yeah, this is a very simple OLS estimator. Yeah, you might remember from econometrics x transposed x inverted times x transposed y. This is exactly what happens here. Next, we can define the OLS residuals. So we can estimate the OLS residuals from this regression here. And let's define the OLS residuals here from as U1. U1 is simply what? It's the dependent variable minus the regressor matrix times the point estimator H1. Yeah, in our OLS framework, you might remember from econometrics, that's simply y minus the regressor matrix x times the estimated beta. We know H1 is a 2×1 vector, right? And the second element is our corresponding estimated Hurst exponent. So let's copy this into Matlab and let's see what comes out. So our point estimator H1, let's see. Here we have it. It's the second element, right? Because the first element is simply the regression intercept, and that's not relevant for us. So we want to know what's the Hurst exponent. And we see obviously here the Hurst exponent is 0.89. So, and this is an interesting thing. Let's plot the original data series. You see here, this is the original data series. And it's obviously a RR1 process that I have simulated here with the first order autocorrelation coefficient of 0.9. So it's a highly persistent process. And this is exactly also what our Hurst exponent tells us, okay? Because 0.89 suggests that the process is persistent. So now we have estimated our regression residuals, and why do we need that? Well, we need to estimate the variance of our Hurst exponent in order to be able to test whether our point estimator 0.89 is it statistically significantly different from 0.5. We know 0.5 defines a process that is independent, respectively memoryless. Now we have just the point estimator, but we do not know if the difference between 0.89 and 0.5 is statistically significant. So that's why we have to estimate first the regression residuals, then we have to estimate the corresponding variance of the regression residuals, which is what happens here. All right, sigma 1 or sigma underscore u1, these are the regression residuals. It's what? It's the vector of regression residuals transposed times itself divided by the length of the residual vector, which is 8×1, right? So the length is 8. It has 8 increments. So, and what is sigma? We have now copied it already in the command window, and we see here in the workspace it is 0.060. Now we are able to estimate the covariance matrix of our Hurst exponent, right? This is what happens here. H1 underscore covariance is what? It's sigma underscore u1. So it's the regression, it's the variance of the regression residuals times what? The regressor matrix transposed itself inverted. So this is simply, you might remember from econometrics classes, it's the sigma hat squared times x transposed x inverted. Yeah, very simple. And what comes out here is, since our point estimator is a 2×1 vector, this guy here must be a 2 by 2 matrix. Let's copy that here into Matlab. Voila, this is what comes out. Okay, and the interesting guy is obviously this guy here. Yeah, so the second element on the main diagonal. What we see here, the first element is obviously the variance of the corresponding point estimator for the intercept term, right? Here, what we see here, above and below the main diagonal, is obviously the covariance between the point estimator for the intercept term and the Hurst exponent. And what we see here, the second element on the main diagonal, is the corresponding variance for the Hurst exponent. So then the t-statistic, and again, we are interested in knowing if the estimated Hurst exponent, or the difference between the estimated Hurst exponent and 0.5, indicating a memoryless process, is this distance here statistically significant, yes or no? So under the null hypothesis, the difference is 0, so we assume that our point estimator is not different from 0.5, and if we reject the null hypothesis, it indicates obviously that our point estimator is statistically significant, different from 0.5, and then in our case larger than 0.5, indicating a significant persistent process. So the t-statistic is then, so again, let's just grab here, copy this code here. Yeah, again, the Hurst exponent is what? It is the second element in this H1 vector. This is what happens here. Okay, we have to define the corresponding Hurst exponent as the second element of the estimated parameter vector. Okay. So then the Hurst underscore exponent underscore standard error, well, it's what? It's the square root of this guy here. Yeah. So this is what we define here. Let's copy that into Matlab, and then we are able to estimate the corresponding t-statistic, which is simply our estimated Hurst exponent minus 0.5, okay, divided by what? Divided by the corresponding standard error. This is what happens here. Let's see what it is. 22.66 in round figures. So now you might remember we cannot use the standard normal distribution here as a corresponding reference distribution. We have to use the t-distribution. Here we see the critical values of the student's t-distribution with corresponding degrees of freedom. And since we have a one-sided test, we have 8 observations, but the degrees of freedom is 6 because we have obviously in our regression equation one intercept term and the point estimator for the Hurst exponent. So that's why we have to subtract 2 and end up with the t-distribution with 6 degrees of freedom as a reference distribution. Yeah? And the one-sided test using a 5% significance level is obviously 1.94. But in any case, we have seen here that our point estimator, obviously, let's see that we get the right window here, that our point estimator of 22 exceeds the corresponding critical value of 1.94 by a substantial margin. What does it mean? It means that we have a process that exhibits statistically significant persistency. Thank you for your attention.